Good morning, everyone. My name is Christina, and we are pleased to welcome you to the Washington Labs Academy webinar series. We hope you find the next hour so useful and informative. We've developed our webinar series to deal with some of the technical and administrative issues our customers face on a day-to-day basis. We recognize that engineering challenges can be complex, and we're always looking for ways to support the technology industry. Before we begin, I'm going to go over a few housekeeping details. First of all, I hope everyone is able to see the title slide on their computer. This presentation is part of our webinar series presented this calendar year. We have muted everyone's microphone to keep the meeting quality as high as possible. A recording of the presentation is underway and will be sent to all attendees, and a training certificate is sent to attendees of the live presentation. A full screen view may be preferred. In the menu on your screen, go to View and then select Full Screen. Use the Escape key and you can return to normal view. We encourage questions during the presentation. You can submit a question by enabling the chat icon at the top or side of your screen and typing your question to the host. We will go through questions at the end of the presentation as time permits. And we'd like to hear from you. You can contact us via phone or email. Please reach out to academy@wll.com or to our presenter directly. So now I'd like to introduce our presenter, John P. Repella, Manager, EMC and Wireless Services, Washington Laboratories Limited. John is responsible for the day-to-day operations at Washington Labs Gaithersburg facility, aiding customers in all manner of product compliance evaluations. John has over 25 years of experience in design, manufacturing, and the testing of systems for regulatory compliance. His expertise spans a full range of product evaluations from IT, medical, machinery, measuring, communications, military applications. John is a member of the IEEE and SAE and is an active member of C63 Standards Committee, participating in several standards working groups. So without further ado, I'm going to go ahead and hand over the presentation to you. John, how are you? John, can you hear me? Hello, John.
Yes, I'm here.
How are you?
Good, good. Are you receiving me?
I am receiving you loud and clear.
Okay, great.
The floor is yours.
All right. Good morning, everybody. I hope that I don't bore you too much with this particular presentation. There's quite a bit of information to cover, and I'm going to do my best to try to address the main points that will be covered by this standard. So in general, many wireless device approval regulations require an extensive set of test and measurement to confirm that the device is compatible with radio frequency spectrum matters. Although not applicable to all countries, the RED cites use of specific harmonized standards to demonstrate compliance, and these ETSI standards describe the test program. Compliance in other countries have similar test program with specific requirements that have a lot of the similar test methods. So what we're going to cover today is the EN 300-328 standard. It's the main standard for all the 2.4 gigahertz modules using wideband modulation, including Wi-Fi, Bluetooth, Bluetooth Low Energy, 802.11, 802.15, all of that. Just in the 2.4 gig. This harmonized standard is performed without a notified body, and it allows for quicker approvals. Once each product is successfully tested, the doc that verifies the harmonized standards can be created. Okay, so essentially the EN 300-328 defines two categories of wideband data transmission equipment. Equipment using frequency hopping spread spectrum modulation, and equipment using other types of wideband modulation, DSS, OFDM, frame-based, any frame-based transmission type. One of the most important things is to have as much information as you can about the radio. You will need this information to develop a test plan. Very often, as a laboratory, we see companies come in that want to test a radio and they don't have a complete understanding of the information about how the radio operates. It's imperative to obtain as much information as possible about the device. We tend, as a lab, ask as many questions as we can, again, because this information is critical to developing the test plan. As far as information goes, a product description, a brief description of the device and how it's used, the type of equipment, Bluetooth, Bluetooth low energy, is it 802.11, 802.15, does it have adaptive or non-adaptive capabilities? Some of these devices have both. How is the device powered? AC, DC battery, rechargeable battery. Types of modulation. So what I stated previously is the frequency hopping systems and the digital spread spectrum systems. The antenna types. Most chip radios just have an integral antenna. Dedicated antennas or antenna systems, which can be associated with MIMO devices, and then the gains of any and all types of antennas used. If it's possible to obtain information regarding worst-case operational mode, it'll help to streamline the test. RF output power, power spectral density, duty cycle. The transmit sequence and the transmit gap aren't as readily available. That's usually obtained from testing, but if that information is known, it's good to provide that. The worst case operational modes continued. Accumulated transmit time, frequency occupation, and receiver category. There's basically three types of receiver categories, which I'll go over later, but they're related to the power. The nominal channel bandwidth, most of these types of devices now have multiple operating bands, operating bandwidths. 20 meg, 40 meg, there's 80 meg, 160 meg, which would be part of the 5 gig stuff, but you'll typically have multiple modulation modes. You need to know all that information because it all has to be checked. The hopping sequence, it's only for frequency hopping systems, and the frequency separation, which is also for frequency hopping systems. Okay, down to the tests. This is a quick and dirty list of the tests that are required, and there are different variations depending on the type of equipment that we're looking at. So, always, first and foremost, RF output power, conducted or radiated, duty cycle, transmit sequence, transmit gap, medium utilization, power spectral density, hopping frequency separation, occupied channel bandwidth, unwanted transmitter emissions in the out-of-band domain, unwanted transmitter and receiver emissions in the spurious domain. And so basically there's an in-band mask that's defined for what's considered out-of-band, an in-band, and then the spurious domain. The big ones, the new ones, are adaptivity and receiver blocking. So quickly, RF power. The RF power is defined as the mean equivalent isotropically radiated power of the equipment during a transmission burst. The maximum RF output power for adaptive frequency hopping systems shall be equal to or less than 20 dBm. The maximum RF output power for non-adaptive frequency hopping equipment shall be declared by the manufacturer and shall be equal to or less than 20 dBm. One of the biggest challenges with measuring power with the new standards is that you now need to look at a burst transmission. You have to sum up all the bursts. It requires a fast power sensor, and it must be first and foremost suitable to the 2.4 gigahertz band, and capable of 1 megasample per second. You also need to keep into consideration the bandwidth. So, there are lots of companies out there that manufacture power sensors, but they don't always have the bandwidth to be able to measure these bursts. So you're basically going to measure each transmit chain of the device between the start and stop times for the individual burst. You're going to calculate the RMS power over the burst using a formula that's stated below. You also want to document the start and stop points because it's going to help you with the duty cycle calculations. Excuse me. So the power summation is part of that formula, where you're basically looking at each one of the samples, and then you're going to sum them up as per the formula. Power is equal to A, which is in dBm, that's the highest burst, maximum ERP calculation. G is the gain of the antenna, and Y corresponds to an additional beam-forming gain if indeed you have a smart antenna system. Most of the new power sensors have software that'll actually help you to make these calculations. It's pretty onerous to be able to do this on a spreadsheet. You can do it, but it takes quite a bit of time. The duty cycle, the TX sequence, and the TX gap. So the information that you obtained from your power measurements is going to be used to provide you with the duty cycle calculations. So it's the sum of all the TX on times between the end of the first gap, which is the start of the first burst within an observation period, and the start of the last burst within that same observation period, divided by the total observation period. So the observation period is equal to the average dwell time multiplied by 100, or the average dwell time multiplied by 2 times the number of hopping frequencies. It should be noted that this requirement is for non-adaptive frequency hopping systems. TX sequence is defined as the period in time during which a single or multiple transmissions may occur and which shall be followed by a TX gap. The TX gap is defined as a period in time which there is no transmission occurring. And depending on the type of device, you're going to have very specific requirements for your TX sequence period and your TX gap. So the TX time shall be equal to or less than 10 milliseconds. The minimum TX gap following a TX sequence shall be equal to the duration of the preceding TX sequence with a minimum of 3.5 milliseconds. Accumulated transmit time, frequency occupation, and hopping sequence. Accumulated transmit time is the total of the transmitter on times during an observation period on a particular hopping frequency. Frequency occupation, it's a number of times that each hopping frequency is occupied within a given period. A hopping frequency is considered to be occupied when the equipment selects that frequency from the hopping sequence. The equipment may be transmitting, receiving, or staying idle during the dwell time spent on that frequency. The hopping sequence of the frequency hopping equipment is an unrepeated pattern of hopping frequencies used by the equipment. So the adaptive and non-adaptive equipment are really the way that this standard is broken down, and everything else kind of falls into place once you know whether you're working with an adaptive piece of equipment or a non-adaptive. It should also be noted that systems can operate as both adaptive and non-adaptive, and so you'll have to keep that in mind when you're doing these tests. So adaptive frequency hopping equipment shall be capable of operating over a minimum of 70% of the band. The accumulated transmit time on any hopping frequency shall not be greater than 400 milliseconds within an observation period of 400 milliseconds multiplied by the number of hopping frequencies that are to be used. The hopping sequence shall contain at least n hopping frequencies at all times, where n is either 15 or the result of 15 megahertz divided by the minimum hopping frequency separation in megahertz, whichever is greater. There's a heck of a lot more detail in the standard itself, but I couldn't provide all that information here. I think it would put people to sleep. Non-adaptive equipment. The accumulated transmit time on any hopping frequency shall not be greater than 15 milliseconds within any observation period of 15 milliseconds multiplied by the number of hopping frequencies n that have to be used. Hopping sequences shall contain at least n hopping frequencies where n is either 5 or the result of 15 megahertz divided by the minimum hopping frequency separation in megahertz, whichever is greater. That gets us to hopping frequency separation. So basically, hopping frequency separation is the separation between two adjacent frequencies. Adaptive and non-adaptive basically have the same requirements. The minimum hopping separation shall be 100 kilohertz. The hopping frequency separation shall be equal to or greater than the occupied channel bandwidth when a minimum separation of 100K. For equipment with a minimum declared RF output power of less than 10 dBm IRP, or for non-adaptive frequency hopping equipment, operating in a mode where the RF output power is less than 10 dBm RP, only the minimum hopping frequency separation of 100 kilohertz applies. Medium utilization. So this is specific to non-adaptive equipment, and it's defined by the formula in percent. So MU is equal to the quantity P divided by 100 milliwatts times DC, which is duty cycle. So power and RF output power milliwatts, the duty cycle expressed in percent, and the maximum medium utilized factor for non-adaptive frequency hopping equipment shall be 10%. Power spectral density. It's the mean equivalent isotropically radiated power density in a 1 megahertz bandwidth during a transmission burst. For equipment using wideband modulations other than hoppers, the maximum power spectral density is limited to 10 dBm per megahertz. That's a pretty standard value that you'll see in most of these requirements. The measurements shall be repeated for equipment being configured to operate at the lowest, a middle, and the highest frequency of the stated frequency range. Power density measurement settings. And so you're basically going to set it to the band, 2.4 to 2.4835 megahertz. The res band and video band are set to 10K and 30K. And your sweep points, which is something that has really never been defined previously, is now has to be greater than 8350 for spectrum analyzers that don't support this number. You're going to have to chunk up your sweep segments equal to the total number of points for that particular span. Your detector is RMS, and the trace mode is a max hold. The sweep time for non-continuous transmissions is 2 times the channel occupancy times the number of sweep points. For continuous transmissions, it's 10 seconds. The sweep time may be increased further until a value where the sweep has no further impact on the RMS value of the sign. So basically, you kind of have to look at the sweep and see if the trace changes. Once the trace stabilizes, you can use that the peak value for your PSD. Occupied channel bandwidth. It's the bandwidth that contains 99% of the power of the signal when considering a single hopping frequency. Non-adaptive frequency hopping equipment with the EIRP greater than 10 dBm, the occupied channel bandwidth for every occupied frequency shall be equal to or less than the nominal channel bandwidth declared by the manufacturer. This declared value should be no greater than 5 megahertz. The measurement is performed on the lowest and the highest frequencies in the band. It's a little bit of a deviation. You used to have to go low, middle, and high. Now you only have to do the lowest and the highest because you can look at the band edge as well. occupied bandwidth settings. So you're going to set the spectrum analyzer to the center frequency of the channel under test. Your resolution bandwidth will be about 1% of the span without going below 1%. And your video bandwidth will be 3 times that res band. A lot of the newer spectrum analyzers actually have bandwidth measurement settings, and you can use the automated settings as configured for whatever span you're looking at. The frequency span 2 times the nominated channel, or the nominal channel bandwidth. Once again, your detector mode is RMS, your trace mode is max hold, and your sweep time is 1 second. You're just going to wait for the trace to stabilize. You'll find the peak value and place the analyzer marker on that peak. Use the 99% bandwidth function on the spectrum analyzer to measure the OBW. If you don't have that capability, the 99% bandwidth is usually equivalent to 26 dB down bandwidth. Transmitter unwanted emissions in the out-of-band domain. This requirement applies to all equipment using wideband modulations other than frequency hoppers. Transmitter unwanted emissions in the out-of-band domain, but outside the allocated band, shall not exceed the values provided by the mask that I have on screen now. And so if you just take a look at it, it's basically the in-band, the allocated band, 2.4 to 24835, and then the requirement is 1 bandwidth on either side. It has to be down 10 dB per megahertz. 2 bandwidths on either side. It has to be down 20 dB, and then everything else falls in the spurious, which is covered in the spurious limits. Out-of-band transmitter spurious measurement setup. So you're going to center the frequency at 2484 megahertz, 0 span, and a resolution bandwidth of 1 meg, video band of 3 meg. Your filter mode, if it's available, is a channel filter. The detector mode is RMS. Your trace is max hold. It's a continuous sweep, and then your points are equivalent to the sweep time divided by 1 microsecond, or 5,000, whichever is greater. You're going to use a trigger mode to you may use a trigger mode in case of video triggering is not possible. An external trigger source may be used. You might be able to use a diode detector as you measure the burst, or you may be able to use a power meter and trigger off the power meter as it's reading its individual burst. The sweep time is 120% of the duration of the longest burst detected when you measure RF power measurements. And it is key to make sure that you understand fully a single burst, because without understanding a single burst, the TX on time, the TX gap, it's almost impossible to really make these measurements. Each segment is evaluated according to the settings above previously. The trigger level will have to be adjusted to select the transmissions with the highest power level. As you move closer and closer to the band edge, you'll have to change your power settings because it won't trigger. You'll just sit there and wait. For hopping equipment, in a normal hopping mode, the different hops will result in signal bursts with different power levels, as I stated. In this case, the burst with the highest power level should be selected. You'll just trigger on that, and then you'll make your spurious measurements. So each segment is evaluated until the entire range of the band is covered. Unwanted TX and RX emissions in the spurious domain. So the level of spurious emissions shall be measured as either their power in a specified load, which would be conducted, and their effective radiated power when radiated by the cabinet or structure of the equipment, or the effective radiated power when radiated by cabinet and antenna in the case of an integral antenna with no antenna connectors. And I realize that a lot of the smaller chip radios won't have an antenna that you can connect to. And so sometimes the manufacturers of the chip will provide a test set that you can use where you can mount it, and they'll actually bring the antenna, the conductor out. But if not, everything's got to be done radiated. The spurious emissions continue. Transmitter and receiver unwanted emissions in the spurious domain shall not exceed the values given in the table below. In the case of equipment with antenna connectors, those limits apply to the emissions at the antenna port. For emissions radiated by the cabinet or emissions radiated by integral antenna equipment, these limits are ERP for emissions up to a gig and EIRP for emissions above 1 gig. So you'd have to do the substitution measurements above 1 gigahertz. And here are the limits. They're defined by ranges. It gives max power and also the measurement bandwidths. As you can see, up to a gig, and then above 1 gig, we go to 12.75 gigahertz, which is basically standard for most of the European radio requirements. The receive range, there's the max power, and that's anything outside that band in that mask. So the measurement settings for 30 meg to 1 gigahertz, 100K, 300K res band and video band. The filter type is a Gaussian or a 3dB. Detector mode is peak. Trace mode is a max hold. And your sweep points are defined as greater than or equal to 19,400 points. So if you've got an analyzer that has points greater than that, or at least that many points, you can do a single segmented sweep. Otherwise, you have to do a little bit of math and then break down those sweeps into chunks to cover the requirements. For 1 to 12 gig, 12.5 or 12.75 gig, the settings are res band 1 meg, video band 3 meg, same Gaussian 3dB filter. The detector mode is peak, trace mode is max, and the sweep points jump to 23,500. So again, for analyzers that don't support this number of points, the band has to be segmented. But if you do have that many points, you can do that in one shot. And so the procedure is any emissions identified during the sweeps above and that fall within 6 dB of the applicable limit or are above shall be individually measured. The following settings will be used for the investigation. So the measurement mode is a time domain power measurement, just a standard power measurement. The frequency of emission is identified during the pre-scans. You're going to select the same frequency, 0 span, single sweep, 100% of the duration of the longest burst detected during the measurement for the RF power. And once again, I'll reiterate, RF power is critical. It's 30 milliseconds for the receive, just in case you need to know that as well. Sweep points, sweep time, microseconds over 1 microsecond with a maximum of 30,000 points, greater than 30,000 for the receive side. Trigger is a video or a manual continuous if you have a continuous signal. Your detector is RMS. Adaptivity, this is one of the new ones. It's a mechanism which allows the equipment to adapt automatically to its radio environment by identifying frequencies that are being used by other equipment. The requirement is only applicable to equipment utilizing the LTB, which is listen. It's actually, that's a typo, I'm sorry. It's listen before talk, and forms of DAA, which stands for detect and avoid. A given hopping frequency is made unavailable because an interfering signal was detected before any transmit on that frequency. This mechanism shall operate as intended in the presence of unwanted signals on frequencies other than those of the operating band. there's a typical setup for adaptivity measurement. So you've got and this is a conducted measurement, I should be clear. The standard also has setups and methodology for doing these measurements radiated, but for time constraints, I just use the conducted. It's the easier of the two and doesn't take anywhere near as long. So you have the equipment under test, a splitter and combiner, to a spectrum analyzer, and then a directional coupler. You've got an attenuator in between a companion device to provide the link, and then you've got an interference signal and an unwanted signal. And so basically you're going to be toggling those interference and unwanted signals after you establish a link to see how the device reacts. So the general methodology, which I just described, I won't go into specific detail, but you're basically going to establish a link that operates just above its minimum required connection length. So you have to kind of play with the signal until it almost drops out, and then you'll bring it back up, and you'll establish that link. The limits are 6 dB. Once you find your power setting for your companion device that links, it'll be 6 dB above that. The power level will be 6 dB above that to provide a standard link. And so then you'll add the interference signal. And once again, the standard has pretty specifics in the appendices on how this is done. So an interference signal, as defined in the clause, is injected centered on the hopping frequency being tested. The power spectral density level of this interference signal shall be equal to the detected threshold. And once again, that detected threshold is what you kind of set the system up to prior to adding the interference signal. So then you're going to verify the reaction to the signal, and you'll use the spectrum analyzer to monitor those transmissions. The EUT shall stop transmissions on the hopping frequency being tested. It's also assumed to stop on this frequency within a period equal to the maximum channel occupancy time. And so again, I reiterate, the RF power measurements are critical because everything else builds on being able to verify the adaptivity and later on the receiver blocking. You add the unwanted signal, and the EUT shall not resume normal transmission on that frequency being tested as long as both the interference and the unwanted signals remain present. Removing the interference and unwanted signal. Upon removal of those signals, the EUT is allowed to re-include any channel previously marked as unavailable. However, for non-listen before talk-based equipment, it shall be verified that this shall only be done after the defined period as per the requirements. And depending on the type of equipment that you're using, or that you're testing, I'm sorry, there are specific levels, specific time frames that the system has to respond to. Receiver blocking. This is, once again, another new one. It's the ability of the equipment to receive an unwanted signal in its operating channel without exceeding a given degradation in performance of the unwanted signal on frequencies other than those operating in the band. For equipment that can be configured to operate with different channel bandwidths and data rates, then the combination of the smallest channel bandwidth and the lowest data rate for this channel bandwidth, which allows the equipment to operate as intended, shall be used. For systems using multiple receive chains, only one chain or antenna port needs to be tested, although the receiver input shall be terminated. So for MIMO devices, you only need to look at one of the receiving antenna. If you have smart devices with beamforming, it gets a little more complicated, and there's guidance in the standard as well for that particular config. The test setup for receiver blocking, it's somewhat similar to the adaptivity. So you'll see an optional section in the middle of that palette. It basically allows you to monitor. I prefer to have the spectrum analyzer in there because you can actually see the signal dropping out, but you don't need to have that because of the requirement of a monitoring device. And so you'll set it up with some type of a payload, and then you'll look to see that it operates as intended. So the general measurement methodology, it's operated at the lowest and the highest operating channels. The blocking signal generator is set to the first frequency as defined by the appropriate receiver category. And so once again, like I said earlier on, there are 3 different receiver categories, and they're based on power. With the blocking sig gen switched off, a communication link is established between the EUT and the companion device. A variable attenuator is increased in 1 dB increments to a value at which the minimum performance level is established. It's very similar to your adaptivity test. The resulting level for unwanted signal at the input at the EUT is then that's established as your minimum power. This level is increased by the value provided in the table corresponding to the receiver category and the type of equipment. And so pretty much across the board, I think that minimum level is increased by 6 dB. I don't think there's any real difference with respect to those requirements. The blocking signal at the EUT is set to a level provided corresponding to the receiver category and type of equipment. This level is verified and noted. This process is repeated for each of the remaining combinations of frequency and level for the blocking signal corresponding to the receiver category and type of equipment. And so basically, you might not be able to see this. You can't really see it. When you're doing your receiver tests, you're actually randomly selecting a signal to have the unit operate at, and then the tables define the signals that are actually brought into the out-of-band edge until you reach the signal of operation. So this next slide actually summarizes the equipment requirements, right? And so RF power, power spectral density, duty cycle, the TX sequencing gap, the accumulated transmit time, frequency operation hopping sequence, the hopping frequency separation, medium utilization, adaptivity, occupied channel bandwidth, the transmitter spurious, in-band, out-of-band, and spurious domain, the receiver spurious, which is I grouped in the transmitter spurious, receiver blocking, and geolocation. And so the geolocation is only for equipment that has the GPS receivers. It's becoming more and more relevant, and I would imagine that the next version of this standard will probably have a definition for specific test requirements. And then you can see U stands for unconditional, you have to do it, and then the C is conditional, and it's dependent on the equipment type. It's broken out by, again, it's broken out by either a frequency hopping system or a non-frequency hopping system, and then adaptive and non-adaptive. So there are permutations of those combinations. And once again, you can actually have radios that operate with both an adaptive and a non-adaptive mode on a hop or a non-hopping mode. And accordingly, you have to test for all of those different combinations in worst case environment. It can get pretty onerous and pretty extensive as far as the testing goes. And so you want to make sure you kind of have all your ducks in a row, because you only have so much time to test this. As a lab, we still would like to try to be profitable, and some of these radios get very complicated. So available resources, the ETSI standards, you can get those, download those for free. The blue guide, or the new approach directive, kind of gives you information on how to kind of approach the test methodology. It also gives guidance on the new radio equipment directive, because there's a lot of stuff that has to be taken care of these days. Any questions? I guess we can open it up at this point. And if you don't want to ask questions to me, you can always drop me a line, and I can either answer it for you or point you in the right direction.
Hey, John. Looks like I got a couple of questions here for you.
Okay.
First of all, do spurious emission requirements vary among the different standards?
For the most part, the spurious emissions requirements, they're the same. 5747 for above and below a gig for a receiver. There may be some different band breakouts, but those specific levels pretty much remain the same. Now, you know, with everything moving into completely being harmonized to the red, there's a general movement for these standards to kind of be in alignment with one another, so that, you know, one standard doesn't say test it this way and another standard says test it this way, and they're in direct conflict. Like I said, the movement really is to have standards become much more standardized, to use a bad word. And so if you look at the companion standard to the 2.4, it's 301.893, which addresses the requirements for the 5 gig devices. The methodology is pretty much the same.
Okay. John, if multiple standards apply because of the presence of multiple transmitters, is immunity testing the same?
Again, with harmonization of these standards, you go back to the immunity requirements, the general immunity requirements as stated by EN 301-489-1, and then depending on the types of radios, the immunity requirements will be specified in the lower level documents. You know, I think there are maybe 30 or 35 different dashed standards for specific equipment in the 489 series. In most cases, the 489 dash series refer back to the dash 1. And what we typically do here in the lab is, if 2 standards differ by radio, we test to the worst case. And that way we cover all bases with one set of tests. And that way you don't have to test multiple times according to different standards to state compliance. You can state compliance unequivocally.
Okay. Are there rules for choosing physical filters for spurious emission measurements?
Are there rules? Not that I'm aware of, but once again, the filtering has to allow you to make these measurements. So, you know, if you're worried about transmitters in the 2.4 gig and you want to look at out-of-band emissions above 2.4 gig with a filter, then you need to take into account all of the losses. But as far as rules go, there aren't any real rules about the filters.
Okay, here's an interesting question. What do you consider to be the most frequent non-compliance?
In most cases, we don't have enough information to actually properly do the tests. We'll be given a radio, and it's a Bluetooth module, and it can also act as a Bluetooth low energy and somebody will forget to tell us that, oh yeah, by the way, it also operates in a legacy mode. And so you have to evaluate that device in all three modes. But if we don't have that information, we can't test to that. And so in most cases, it's the pitfalls that occur as a result of having insufficient evidence or insufficient information to be able to test these devices.
Okay. Here's a question. You're going to have to help me with this one. I don't really quite understand. It says, in regards to adaptivity for LVT-based, how is the load-based equipment CCA and extended CCA differentiated from off time, since they might be included in the nominal off time?
Ooh, that's a good question. You know what? To be honest with you, I'm not sure about that. I just know that for the CCA, the minimum requirements are 10 milliseconds and 3 milliseconds for the TX on, TX off gap. But honestly, the extended, I'm not sure. I apologize. If you want to send me an email, I can certainly research that and get the answer for you. I haven't been tasked with that particular specific type of test. It's a good question.
Okay. I guess we have time for one more, right?
Sure.
Let's see. How long is the test data considered to be valid if the application filing is delayed?
As a rule of thumb, it's usually 1 year from test. And the only reason I say that is because that's what we use from the FCC. So if we were to submit an application for a radio tested in the United States, if the data is older than a year and there's still no formal filing with progress to a listing, then it'll have to be retested. And I think the FCC takes that line only because technology moves so fast. Now, with respect to the EU and the ETSI standards, there's no clearly defined time frame or timeline because so much of this stuff is still moving. The databases are coming up to date with the formal listing of these devices, and so it may change within the next, or actually they may adapt a time frame for the relevance of data. But right now there is no defined time. As a laboratory, we use a year.
All right. Well, it looks like we've answered pretty much everybody's questions here. I'm going to go ahead at this time to switch gears quickly and go over some of our upcoming training. So you can link to us at wll.com/us/academy and find information on all of our upcoming webinars and resident courses. Quick look at what's coming up. We have product safety webinar tomorrow. Session 4 is going to cover thermal and fire safety. Our classes are held Tuesdays at 11 a.m. Eastern Time for product safety. Our next wireless technology webinar series continues with broadband devices. That's going to be presented by Mr. Michael Young, and that'll be on the 10th. So that's this Wednesday at 11 a.m. Our last offering of the MIL 461 hands-on course, May 16th through the 19th at our Gaithersburg lab. Note that our EMC MIL 461 webinar series completed in early February, so recorded playbacks are available from our website. We have environmental webinar series, MIL Standard 810, in development. I expect that we'll be seeing the release of that sometime pretty quickly. Battery University Battery Technology series, by popular demand, we have a 4-part webinar series, and it's going to run again in September. See elsewhere happening out there. Today in San Jose, California, we have the IEEE Symposium on Product Safety Compliance Engineering going on. And then Washington, D.C., the week of August the 7th is the IEEE EMC Power Signal and Power Integrity Symposium. If you plan to attend, we're going to have Steve Ferguson there from Washington Laboratories. You can stop by and say hello to him. All of our webinars and recordings are available for purchase from our website. The webinars are available as multi-part series events, so you can choose and join in on detailed discussions on any of the class topics. If you sign up for a whole series, you receive a 15% discount. We'd also love to hear from you with suggestions on future topics we can present. We also provide customized training at your place or ours, so go ahead and visit our Academy training page and check out the latest on course topics and dates. John, I think, let's see, well, there's a question about slides. Yes, all of the slides, the presentation, as well as the recording of the presentation will be sent to all attendees. So, John, I don't see any other questions. I guess we're going to go ahead and end the event at this point. Thank you very much.
Again, just quickly, if you have any additional questions, don't hesitate to send an email. I can certainly find the information if I didn't have it readily available. And the CCA question was actually a good one. I'm going to go look for that immediately. So I do appreciate that. Thanks again for your attendance.
All righty, everyone. At this point, I'm going to go ahead and end the event on behalf of myself and Washington Labs Academy. I'd like to thank everyone for their attendance and participation. So enjoy the rest of your day, everybody. Bye-bye.